Alright, hello and welcome back to these slides. We're going to finish them up and start some cool new ones as well. So we were talking about game theory, how to mathematically specify why some games end up the way they do. And the word game is a bit more broad than we maybe thought it was before. Okay, so we talked about Nash equilibrium and how to solve the prisoner's dilemma problem and why it ends up the way that it does, which is counterintuitive. And now we're back down to here. So what I want to talk about first, of course, is the final, because it's coming up. We are in week 15 right now, and technically week 18 is the week of the final. That's finals week. All right, so I have made a module for this, and I will make it available eventually. And yeah, here is the final info page that you can click on and see stuff about the final. Okay, so this is what you want to look at. And so yeah, the final is going to be on Canvas, just like the midterm, from the same times as the midterm, starting on May 18th. That's the Tuesday of finals week. Here it is. It is Tuesday. Okay, and the final is going to be made available 2:30 p.m. May 18th, and it's going to be available until 5:30 p.m. May 19th. That's the Wednesday of finals week. Okay, so you have over 24 hours to do it, but it's starting on a Tuesday. Okay, Tuesday to Wednesday. Keep that in mind. Yeah, so it's going to be a 2-hour exam because finals at this college are supposed to be scheduled to be like an hour and 50 minutes. So I'm just going to give you 10 extra minutes to do whatever you want for extra time. Okay, so yeah. I'll just give you 10 extra minutes to use them if you need them. I'm going to design the test as if it were going to take an hour and 50 minutes. I'm not going to give you a 2-hour test and make you do 10 more minutes of work. You'll just get extra time. And so, yeah, you are next wondering, I'm sure, about what the topics will be. So just like the midterm, I'm going to give you an essay to write about some stuff. And then also I will ask you Python coding questions, okay? So those are the two things you should expect to see on the midterm. For the coding questions, I want you to prepare to write code, and you're going to paste it into a Canvas text box. So just get ready, get idle open before you even start the exam, okay? Be ready for that, okay? And so yeah, the place that I'm going to get these questions from is the programming assignments and also the in-class examples. So everything that I've done in class, all that stuff, and everything that you're doing in your assignments, all those things are fair game for the test. Okay, so I could ask you similar things there. Yeah, so that is the time, that is the content, that is the final. Let me know if you have any questions about that, but that is, I think, all I wanted to say there. And so, yeah, let's continue with talking about game theory. Okay, so I told you last time that there were two main kinds of games: cooperative games and non-cooperative games. Cooperative games are where you want to make like a group, you want to form an alliance. Non-cooperative games are where that's a bad idea, or you only ever do it if you're forced to. Okay, so that is the idea. Okay, so cake cutting. You maybe have done this with like a sibling, or when you're sharing a sandwich with somebody, or a burrito. When you cut something, like, who's to say, if you're about to share this cake, who's to say that you can't just make a cut that looks like this? You're like, I get this half, and you can have this tiny piece right here. Yeah? That is a bad idea with the cake cutting example. Okay, so here's the game. Maybe you've played it again with like a sibling or something. It's like one person cuts, so like I cut the cake, and then you, the other person, gets to choose which piece they want. Okay, so that's how you play this cake cutting game. I'm sure you might have played it before. All right, so that is the game, and the internet's not going to tell me. I've looked long and hard, but it won't let me know whether or not this is a cooperative game or a non-cooperative game, because the cooperation is kind of forced on you. So I'm thinking non-cooperative, but I'm still not sure. Okay, so this is the game, and what is the optimal strategy, right? what is the best way to guarantee that you get the most cake? Because if you cut it in this way, with this tiny piece and this big piece, the other person's going to pick this one, and you're going to be left with the tiny piece. Your optimal strategy, what you're forced to do, is cut this cake directly in half, okay? Because if you do that perfectly, then you both get to share. The other person, doesn't really matter which side they pick. You both get the same amount, okay? So that's the cake cutting game, and this is, of course, the optimal strategy if you want the most cake, okay? Because you want to optimize how much cake you get. And so this is called the cake cutting game, and it's an example of Pareto Optimality. Pareto Optimality gives us a way of talking about how intuitive, how nice a situation is. So for cake cutting, like here's our cake, what we were doing was allocating resources, right? And in this example, our resource was cake, which is a fun one to do. So a resource allocation, so like cake cutting, a particular way of cutting the cake, it's Pareto optimal when if you were to change that allocation just a little bit to give somebody a bit more, somebody else a bit less, if that always leaves somebody worse off, okay? It's optimal if changing it leaves somebody worse off, okay? So that's a very utilitarian concept. Mill would enjoy that because we're looking out for everybody. An allocation is Pareto optimal if that means that changing it makes somebody less happy, all right? That is the idea. So even if it makes another person more happy, if someone else was less happy, that is Pareto optimal, okay? That is a nice thing to want. It has the word optimal in it, right? So let's talk about how you can make a Pareto optimal allocation for cake cutting. So the question that we ask again is, because of this definition, what kinds of cuts leave someone worse off if you change them? Let me make sure I'm recording, yes. I clicked something, sorry. I think it's still happy. Yeah, we're good. So what kind of cuts leave someone worse off if you change them? So here's a horrible cut. Like, you are definitely getting stuck with a smaller piece, right? But, and then your sister is going to have this other one. But what if you change this cut to be this one instead? The other person's still going to pick this one because it's bigger, and you get more. But they just got less. So this is actually a Pareto optimal allocation, isn't it? Changing it left someone worse off, the person who would have gotten the bigger piece. See that? So that's Pareto optimal. What about cutting the cake in half? Is that Pareto optimal? Well, sure it is. Because if I change it, if I change the cut to be not like that, but one of them's like this instead, that means this side's slightly bigger. That means that whoever's stuck with this piece, the person who cut it, right, is going to be worse off. So it just so happens that cutting the cake in half is Pareto optimal, and so is everything else. Isn't that weird? That's an interesting definition, isn't it? So every allocation for cake cutting is Pareto optimal, if you think about it that way. So that doesn't solve the problem, but it's an interesting thing to notice, okay? But we can use Pareto optimality to talk about now the prisoner's dilemma, because the Nash equilibrium that we found is a non-Pareto optimal outcome, right? There is a way to make people better. There's a way to change the allocation to give everybody no time in jail at all, right? So that's not Pareto optimal, but it's the Nash equilibrium. It's what's really going to happen. And this helps explain like why the prisoner's dilemma makes no sense at all. It's kind of paradoxical. It's counterintuitive because it doesn't follow this pattern, okay? So sometimes it's good to use this definition when you're talking about games, okay? So that's Pareto optimality. Let's move on now to riding in a taxi, okay? So this is a fun little game. Again, not really a game, but you can think of it as one. It's modeled as a game, all right? So this one's cooperative because you're sharing a taxi with somebody, like you're sharing an Uber or a Lyft with somebody else. And here's the idea. Alice and Bob These are two people. They're about to share a taxi. So here's the idea. I don't know. Here's my best drawing of a taxi. Whee! It's got its little meter on top and everything. Taxi's sitting here with Alice and Bob, A and B. And the idea is, I mean, they both live on the same, on the way to each other's house. So like Alice lives like over here, and then Bob lives over here on the way. Okay, so here's Alice's house, here's Bob's house. And so they're sharing the taxi because their routes are on the same way. The taxi would have to take the same streets, right? So yeah, this is the setup. And here's the idea. We want to split the cost of this taxi ride with both people because the taxi just pays by distance and time. It makes no difference how many people are sitting in the car if there's enough seats. Okay, so here is the idea. If Alice got the taxi to her house by herself, it's closer, so she'd only pay $5 for the taxi ride if she just got in by herself to a separate taxi. And if Bob got a taxi by himself, he'd have to pay $12 because it's a bit farther to his house. Okay, that's the idea. And remember, because it's a taxi, they just pay by time and distance. The fare for both of them together, because it's going to be Bob that pays at the end, it's going to be $12 still, yeah? Because they went the same distance. So, the question is, the game is, how much should Alice pay to fairly split the bill? And that also says how much Bob would pay. Because it shouldn't be 6 and 6, right? Because if Alice paid $6, she pays more than if she would have just got a taxi by herself. And if Bob pays $6, he's definitely the winner there. He's saving a whole lot of money. So that's not fair. 6 and 6 is not fair. I think you can see that. So we need to fix this. And there's a way. Okay, there's a trick. So let's figure this out with a tool called the shapely value. Okay, this was named after somebody who discovered it. And so this concept will tell us the answer. It's called the shapely value. And the way you determine this shapely value is you consider the different orders in which these people could have paid. Okay, so it's a weird little process, but it's going to solve the problem. So we consider the permutations of who is going to pay the remaining bill in what order, and then we take the average. Okay, so here's the idea. So either Alice goes first, she pays first, and then Bob pays, right? Or Bob pays first, and then Alice pays. All right, so this is the idea. If and they're each paying like the amount that they would have paid normally. Okay, so if Alice paid first, she's setting her $5 down, and then Bob's going to have to pay. So Alice pays the $5. Bob then pays the rest of the bill, which is going to be 12 minus 5 is 7, right? So Bob pays 7 in that case. Then, opposite, if Bob were to pay first, then he would pay $12. Okay? He'd pay $12, and then Alice would be left with the rest of the bill, but there is nothing. So Alice would pay $0 in that case. Okay? If Bob paid his sum first. And so this is the setup. And what we can do to figure out the fair cost for Alice to share this taxi is we average these two outcomes, these two possibilities. $5 and $0 averaged together is $2.50. And this is the fair price for Alice to pay when she shares the taxi with Bob. Okay? It should be less than $5, so 6 and 6 is a horrible idea. And yeah, that's the idea. So if Alice pays $2.50, that is a fair price for her, and that is how we determine it using the shapely value. All right, so we just determine, or we consider the different orders in which these people could have paid, and they pay their full price, or whatever's left in that order. Okay, so that's fair taxi rides. It's a fun little game, and you can use this with friends to determine how much money that they should hand over to you, right? So the next and final thing in this set of slides is kind of like the pièce de résistance. It's the best, coolest example. It's how to solve the game of tic-tac-toe, how to pick the best next move to play, always. If you have a computer, you can do this. It'll take a while to figure this stuff out by hand, but I'm going to teach you how you can program a computer to play tic-tac-toe perfectly, okay? Feel free to watch this video. It's you can learn a lot of things from it. So the game is tic-tac-toe, right? It's a real game this time, and we're going to search for the best possible move to play in this situation. And we're going to use a method called Minimax, which is a fun little word, and that will find this optimal strategy. So let's pretend that we are starting with this board right here, and we are X, okay? We are X, and we need to figure out the best move for us to play right now, okay? And because we can use a computer, the idea is we simulate the rest of the game, all the different ways that the game could be played from here, okay? And then we're going to do some fancy Minimax stuff to that simulation. So let's simulate it first, and then we'll come back to the slide and talk about how Minimax is going to solve this problem. So our state, our initial state, is going to look like this: X, X, O, 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 X, X. Okay, and now it's our turn, so we're X, and we could go in many different places. We could go here, here, or here, 3 different ways. So if we're going to simulate this, let's just try all the different ways. The game could go like this, or like this, and we can put an X in each spot. And let's see if I can save myself some time by copying this. Oh yeah, I think we're in business. Beautiful. Lovely. All right, so yeah, the X could go here. Oops. X could go here, here, or here. Those are the 3 different options for us. And so this one's already a winner. There's nothing after this. You can't move after you win. So these ones, though, they have options. O could go in one of 2 spots now. See? And O could go in one of 2 spots now. Boop, boop. So we have, for this one, whee. Oh no. Try again. Interesting. I wonder why it's unhappy. Well, I can just put it back that way, I guess. It must be trying to copy something else. Who knows? Let's try this one. Wow, it's really unhappy. I'm not sure why. How about if I just say copy paste? Yeah, that works. Whee. Happy now? I guess so. All right. So let's do all the different possibilities, because now it's O's turn, right? O could go... oh no, what happened here? There's supposed to be an X here. My bad. And there's supposed to be... This one worked, right? No, it didn't. That's the weirdest thing. Oh well. Okay, so now it's O's turn. O could go here, or here, or here, or here. Those are all the different ways that the game could be played up until this point, right? And so it looks like this one could also have one last move, because it's still nobody's won yet. So X could go in that last spot. X, O, 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 X, 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 X. All right. And so here is the complete game state for us. And here are the places where we win. And let's see here. Oh, there's also one more state right here, right? O wins in this one, but not this one. X, O, O. X would be forced to go right there and win. Right? So X wins there too. But O, let's do O and rainbow, I guess. O wins here and here. All right. So now we analyze. We use this thing called Minimax. So the idea is when it's our turn, we make the move that maximizes our chance of winning. Okay? And then when it's our opponent's turn, we assume that they're going to make the move that minimizes our chance of winning. Okay? We assume that our opponent is really, really good. So they're always going to make the best move possible to them at that point in time. All right? So the idea here is we're definitely going to pick this move. But let me tell you why. Looking at these, yes, there's a way for us to win still, but we know that O is going to pick this one. So we weight this one as like this entire board as -1 because we lose here, right? So this one's like -1. This one's like +1 because we win, but we're minimizing because it's O's turn. And so the whole board, we like give it a number, it's -1. All right? This one's +1. And then this one is again -1 because even though we win here, when it's O's turn, it minimizes the game. We know that it's going to pick this one and we're going to lose. We're most likely, almost certainly going to lose unless O is not paying attention. So we don't like this one. We don't like this one. We're going to pick this one to do. Okay? This is the one that we're going to go with. It is the best possible move for us because when it's our turn, we maximize our possibility. And this is like the score. Okay? So even though there's ways for us to win, we're going to assume that O doesn't like those ways. And they're going to try and get us to lose in the other situations, in the other states. Okay, so that is Minimax. And that is how you can actually write a program. I'm making students in one of my more advanced CSCI classes write a program to do this right now. So yeah, that is Tic-Tac-Toe, the best way to play the game. All right, so that's the end of these slides on game theory, and I have another set for you now. So this topic is called recursion. That's the first one I'm going to start with, and that leads into beauty as well. So I kind of am going to put them together because I think recursion is beautiful, and I hope that I can convince you too that it is. Okay, so let's get started and talk about this magical thing called recursion. So let's start with this slide. I guess there's a question, a hidden little question here. Is it circular reasoning? Because we know that's a fallacy, right? Isn't it just circular reasoning to solve a problem in terms of itself? Like, okay, let's solve the problem by solving the problem. How does that work? The answer is, it may or may not, depending on what you mean by in terms of itself, okay? It's possible if the problem gets smaller and smaller and smaller, you'll actually be able to solve it. Even though you're solving the same problem. It looks the same, but it's smaller. That is the beauty of recursion. It lets you solve these problems, okay? And this is an example of the Tower of Hanoi, which I encourage you to look up. It can be solved with recursion, and the idea of this game, if you haven't heard it before, is that you got to put these pegs, you got to move this entire stack of pegs over to here, but the rule is you can't put a smaller peg on top of any others, and you have to move one peg at a time. So you can't put a smaller peg at the bottom and then put a bigger one on top of it, okay? So this one's definitely forced to go right here, and then the one underneath it can't go on top. It's got to go over here, and then you have to somehow like maneuver all these around so that it ends up looking like this over on this peg, okay? That's the Tower of Hanoi. It has a very natural solution using recursion, all right? So the answer to this is no, it's not circular reasoning as long as the problems get smaller. As long as the problem gets smaller, let's say. You're good. All right, so the idea of recursion, the definition of recursion is that you are solving a problem in terms of smaller versions of itself. Like, okay, here is a smaller problem to solve. It looks like the same thing, but it's going to lead me to the answer soon enough. Like there's one that is the end case. All right, a smaller problem to solve is solvable. That is the hope. Okay, so the idea with recursion is you're going to find a problem And that problem is going to exist, that same exact problem will exist inside of itself. Isn't that weird? So you find this problem inside of itself, yeah? And we call that a subproblem, okay? We're not very fancy with our names. That smaller problem, it's called a subproblem. So here's our big problem, and there's a way to break it down into a subproblem that's easier to solve, okay? And then we go off and we solve this one, and that will lead to the answer, hopefully, of the original bigger problem, okay? That is the idea. We use that answer to our subproblem to solve our original larger problem. That is the answer. Okay. So, yeah, I guess what I want to do now is give you the quintessential example of recursion, and that is factorial. Okay? So, we're going to talk about the factorial problem in depth and come up with a recursive answer for it. Okay? So here's the idea. We want to find the factorial of a number, and that happens to be a recursive problem. So you remember what a factorial is, right? 5 factorial, it's that exclamation point thing. 5 factorial equals 5 times 4 times 3 times 2 times 1, right? It's useful for like probability stuff. You might have learned it under that umbrella in a math class. So that is factorial, and I'm going to show you that this is a recursive problem. It has an answer in terms of smaller versions of itself, okay? So remember now, what is the problem? The problem is finding a factorial, solving the factorial problem, something exclamation point. So, without looking at the rest of this slide, can you find a smaller factorial problem, a smaller factorial solving problem inside of this one? Can you do it? That is my question to you. And if you stare long enough, you might find this one, right? Because what's that other than 4 factorial? Do you see that? That is the key thing right there. We just found a problem inside of itself. There's also other ones, like there's 3 factorial, there's 2 factorial, there's 1 factorial, but we like the next smallest. That's a really good one for us right here, okay? So it just so happens that we can use that 4 factorial to build up the answer of 5 factorial, because we can just replace it with all that. So 5 factorial, we've just noticed, it equals, right? It's equal to the 5, that's the one thing that's not included, times 4 factorial. And there's a smaller factorial problem. See that? A smaller factorial solving problem. All right. And this generalizes to every other number, right? Almost every other number. Because if you had 7 factorial, that's equal to 7 times 6 times 5 times 4 times 3 times 2 times 1, which is still 7 times 6 factorial. You see the pattern here. You got this number, you got it over here. And then you have that number minus 1 right next to it. You see that? That's the pattern. So this generalizes to compute the value for n factorial. Just give me some number n, I can tell you what n factorial is. You see that? That is the idea. So what should I put here on this right-hand side? Maybe pause the video, take a second to think about what this should be, because this is the key step right here. How do we go from this to a generalization formula? And this is something that we can program, okay? That's the hope. So it's these match, and then it's one less. So we put an n. This is n times, and then we do one less factorial. That is how we can define the factorial problem in terms of smaller versions of itself. It's beautiful, and this is the answer, right? This is the answer for 5 factorial. It's the answer for 7 factorial. And this is called the recursive case. Because recursion is when you do the same thing, a smaller version of the same thing inside of itself. And there we are doing it right there. So this is called the recursive case. But we're not done yet. In addition to this recursive case, we need what's called a stopping condition, or the fancy term is called a base case, because this is not the full answer. Let me show you. Let me just do it down here, I guess. Because if we said, oh yeah, let's follow this rule to calculate any factorial, we'll never stop. Because we'll be like, oh yeah, 5 factorial, that's, okay, following this rule, n is 5. 5 times 4 factorial, sure. And, oh, what's 4 factorial? That's 4 times 3 factorial. Oh yeah. Okay, let's use this rule again. What's 3 factorial? It's 3 times 2 factorial. Okay, what's that? That's 2 times 1 factorial. Okay, what's that? Well, following this rule still, that's 1 times 0 factorial, which actually exists, defined to be 1. Okay, what's that? Keep following the rule till the end of time. That's 0 times negative 1 factorial. Oh, okay, the final answer should be 0, right? That is wrong. We don't want to do that. We don't want to get there. So we want to stop before this. We can stop it here at 0 factorial if we want. We could also stop it at 1 factorial. Okay? Either way, we just need to be able to say, like, I'm done here. I know the answer to 1 factorial. I don't have to try this rule anymore. I'm finished. And so the goal is to just be like, okay, when you're right here, when you're trying to figure out what 1 factorial is, don't do this. It's just 1. Let's just call it a day right there. That's our base case. That's our smallest little case, our stopping condition. Okay? That is the goal. So we have to use that second rule, okay? Normally we use this for every number except for 1. If you're trying to calculate 1 factorial, we're going to say that that is just immediately 1, okay? And I hope you see why we need that. Otherwise we just keep on going, trying to figure out the factorial of -2, -3, -4, on and on forever, even after we multiplied by 0, okay? This is called the base case. It lets us stop. It's like, okay, yeah, here's the answer to 1 factorial, plug it in, now we can use this one. Now we get the answer back to this one, plug it in, and so on and so forth, okay? This is called the base case. And that stops the recursion. It's a stopping point for us. There we go. That is the idea, okay? And whenever you're looking for a base case, if I'm asking you to solve a problem recursively, you want to think about when you know the answer immediately. When do you know n factorial without ever having to try n minus 1 factorial? And the answer is here. 1 factorial, we just define that to be 1, call it a day. Also 0 factorial. If you wanted to cover all the bases, you should probably use 0 factorial as well, because otherwise this won't work with it. But this is good enough for us, okay? That is the factorial problem. Okay? So now comes the extra fun part. I have written things in terms of variables and just like checking things. That's a program, isn't it? So let's write a function that computes this factorial, or it's going to be like def fact of some number n. That computes, it should give back n factorial. Returns it. Okay, so we're about to write a function that does this. Just here, I'll code it up next time. Functions are the main way of solving a recursive problem in code. And because it's recursive, what does it mean to solve the problem? Like, okay, I'm asking for fact 5. What does it mean to solve this problem inside of itself? Well, that means you call yourself inside of this function. A recursive function calls itself. It's going to ask for like fact 4. It's going to make a call to itself, but with a smaller number. That's the key. Okay? And so, yeah, a recursive function, it calls itself because the problem you're trying to solve is defined in terms of itself. It's so natural, okay? It's going to be weird the first time we do it, but I'm going to try and make it seem natural by the time we're done with this little section. All right? So def fact n, and now we just look at this. We're either in the recursive case or the base case. Let's figure it out and return the answer. Are you ready? So let's check for the base case first. If n is equal to 1, well, we know we're in the base case. We're trying to calculate fact of 1. So the answer immediately, we know to give it back, is just 1. Okay? Return 1. And that's all well and good. Else, This is the recursive case. What do we do? Well, we just follow this. We have a number n. We want to calculate the factorial. We know this is the pattern. We want to multiply n by n minus 1 factorial. Are you ready? So let's do that. We're going to be like, okay, return n times, and let's just make n minus 1 factorial up here and save it. Save it in like an x. X equals, okay, what's n minus 1 factorial? How do I get it? I call myself. In the function I'm defining, I call myself fact of n minus 1. See that? So x holds this answer, fact of n minus 1. That's an x right now. I can multiply that by my n, and I've just made the final answer for the big original number n. Didn't I? Isn't that crazy? Return n times x. That's the answer. But look at this. Isn't that weird? We're making a call to ourselves right there. That is the secret. That is how recursion works. And this, if you type this into Python, I encourage you to try it. We'll do it next time. If you type this in and said something like print fact of 5, it's going to return to you. It's going to output the right answer. It's going to give you back, what is it? 5 times 4 times 3 times 2. I think that's 120. Okay, it's going to print 120. It's going to work. Because it keeps calling itself, it'll eventually stop, and then it'll build back up its answer. Okay, so that is where I want to stop today. We'll pick this up next time, and I'll show you, like I'll draw diagrams, we'll code this up in Python actually, and I will show you exactly why this is working. Okay, even though we've gained some intuition before, I'm going to show you why this code is allowed to work the way it does and how it works. Okay, because that will help. So yeah, we're going to come back to these slides next week. But hopefully that was a fun little introduction to recursion, and hopefully you're starting to get a sense of how cool this is. Like, okay, I just need 2 rules, I've solved this problem. That's beautiful. I don't need any loops. I just call myself. I think it's beautiful. Okay, so that is where we'll stop for this lecture, and I will see you in the programming lecture.